The first fundamental theorem of calculus tells us that if the function is continuous on a closed interval, then f is the antiderivative of the function f on the interval from a to b. So what this tells me is that if I have the integral from a to b of f of x dx, then f is the antiderivative. So I would have the antiderivative would be f of x. So I need to evaluate the antiderivative from f of b minus f of a. That's it. So more notation. If I have, so this is how we write this, is that from a to b of f of x dx, we would say that f is the antiderivative function, and we're going to evaluate it from from a to b, okay? So another way to write this is like f of x evaluated from a to b, or f of x evaluated from a to b. And then when we do that, we just plug in the upper bound and the lower bound so into our antiderivative. So f of b minus f of a. Okay, so the first fundamental theorem of calculus is used to determine the exact value of the area underneath the curve. So we're actually going to like be able to calculate that without me saying like, you know, the area of this function is 7 and this part of the function is 4. We're just going to calculate it for real. Okay, and so another, oh, I think we have an extra here. So the definite integral, since it gives us f of b minus f of a, I think of that as like the original function. So it's the difference or the change in y values of the original function. So f of b, sorry, minus f of a is equal to the net change. So the change in y of the antiderivative. So the original function. Okay. If you're thinking about like taking a derivative, it's like, so it's like if we were taking the integral of velocity, then we would be finding the net change of the position. Okay. All right, so we're going to evaluate a bunch of these. I'm going to try and go relatively quickly. Okay, another thing to remember is that for a definite integral, it gives me a constant, so I do not need a constant of integration. So it takes care of that for me. Okay. So we are plugging in, or we're evaluating x squared. So let's just draw it from 1, 2, 3. So x squared would be 1, and then this would be 9. 9 and 1. So we're going to evaluate the area under the curve from x equals 1 to x equals 3. Okay, so we do this by taking the antiderivative. So the antiderivative of x squared is x cubed times 1/3. Usually we have to write plus c, but what we're going to do is evaluate from 1 to 3. Okay, so we're going to say that next we have to evaluate with our bounds. So we have 1/3 times our b is 3, so 3 cubed minus 1/3 times 1 cubed. And so I get 9 minus 1/3, which is 26 over 3. I just got that on another problem too. Weird. Okay, next up. Here's crazy day. All right, we have from 0 to 4 of the square root of x plus 2. And so I'm going to take the antiderivative. But first, I'm going to rewrite it because I hate square roots. So x to the 1/2. Hate is a strong word. I dislike them when I integrate or when I take the derivative. Okay, so we're going to take the antiderivative, giving us 1. Oops. Oh, I just tried to take the derivative. Okay, raise the power, so 3/2, divide by 3/2, which is the same as multiplying by 2/3. And then we're going to add the antiderivative 2 is x to the first power divided by 1. And then we're going to integrate from 0, or evaluate from 0 to 4. So I get 2/3 times 4 to the 3/2 plus 2 times, again, 4 to the 1. Then I need to evaluate with the 0. So I'm going to subtract out the same thing except for 0 for x. 2/3 times 0 to the 3/2 plus 2 times 0 to the 1. Okay, and I can see right now that everything in the green is going to go to 0. So I end up with 4 to the 3. The square root of 4 to the 3 is equal to 8. It's 64. The square root is 64. So 2 over 3 times 8 plus 8, giving me 16 over 3 plus 24 over 3, which is 40 over 3. Okay, I want to go back and talk about the constant of integration. So if I have the function from a to b, the integration from a to b of f of x dx, and I evaluate my antiderivative, I get f of x plus my constant of integration, and I need to evaluate this whole function from a to b. Okay, so then I'm going to say that I need to substitute in b for x and then subtract out f of a. So I do f of b plus c minus f of a plus c, distribute, and we get f of b plus c minus f of a minus c. C's cancel, leaving us f of b minus f of a. That's why we don't need that constant of integration, is that it cancels itself out. Okay. Ooh, workout. Okay. Up next, we have the sine x from 0 to pi. Sine looks like this. Starts at 0, goes up to 1, and then goes back down to 0 at pi. So we're just getting this area underneath the curve here. So the integral of sine x, remember I like to use the, sine x, the antiderivative would be negative cosine x, evaluated from 0 to pi. So I get negative cosine of pi minus cosine of 0. Cosine of pi is negative 1, and then the negative on the outside. So negative 1 minus the cosine of 0 is 1. I did something wrong here. I need to subtract a negative. So my cosine of 0 is negative 1. So I get positive 1 plus 1 gives me 2. So the area underneath the curve from 0 to pi is 2. That's really nice. Okay, so from the integral from negative 2 to 3 and of x squared minus 3x plus 1. Okay, integrate. X cubed, we're going to divide 1 divided by 3 minus 3x raised the power to 2, and then divide by that power, plus 1x. The power is now 1, so we're going to divide by 1. And we're going to take the integral from -2 to 3. All right, so evaluate. I get 1/3 times 3 cubed minus 3 over 2 times 3 squared plus 3. So remember, you plug in 3 into for every x, and then we subtract out the function using the value of -2. So 1/3 times -2 cubed minus 3 over 2 times -2 squared plus -2. All right, simplify. I get 9 minus 927 over 2 plus 3. And then a negative times a negative is going to give me a positive, so 8 over 3. And then, see that 2 squared is positive, and then a negative times a negative is going to give me another positive. So I get 4, 3, 12 over 2. And then a negative times a negative is going to give me another positive, so plus 2. When I evaluate, I get 55 over 6. I just definitely tried to flip over my paper on my iPad. That doesn't work. Okay, next up, using an absolute value. I always use a piecewise function. So I remember that my h value is 3, and it looks like my k value is also, actually, I'm going to rewrite this. The integral from 1 to 4 of negative absolute value of x minus 3 plus 3, okay, dx. And so I can see my h is 3, my k is 3, and I have an a value of -1. So my vertex is going to be at 3, 3. And then I have a regular old scale factor, but negative, so it's going to go down like so. A slope of a positive 1 and a slope of -1. Okay, so on the left-hand side, the equation for the line is x minus 3 plus 3 with a positive 1 slope. And the equation for the right-hand line is -x minus 3 plus 3. Okay, so I am going to evaluate the integral from 1 to 4. So from x equals 1 to x equals 4. So I can see at 3, the graph changes equations. So I'm going to evaluate from 1 to 3 using the blue equation. So x minus 3 plus 3 dx plus from 3, where we left off, to 4 of -x minus 3 plus 3 dx. Okay. All right. So I'm going to simplify this. So -3 plus 3 is x dx. Look how nice that is. From 3 to 4, we're taking the integral of, and what I'm going to distribute, I get -x plus 3. So I get -x plus 6 dx. Now we're going to take the integral of both 2 times. Okay, so the integral of x is x squared, and then divide by 2. And we're integrating from 1 to 3, plus the integral of -x squared, and then we have to divide by 2, divide by the power, plus 6x, divide by the power, which is 1, and I'm going to group it like that. So from 4 to 3. Okay, you can also write it like this, like just put your function in parentheses, and then say that we're going to evaluate from 3 to 4. Okay, so time to substitute. So I'll write the first one in purple. So we're going to substitute in 3. So I get 1/2 times 3 squared minus 1/2 times 1 squared. Okay? And then the second function, we're going to subtract everything. Whoa, now. Oh, no. We're going to add negative 1/2 times, plug in 4 squared plus 6 times 4. And then we plug in the second bound. Okay, so we have to subtract everything here. So negative 1/2 times 3 squared plus 6 times 3. Okay, time to evaluate. So evaluating, I should get 9/2 minus 1/2. And then we're going to add, but we're actually really subtracting because of the negative. 16/2, which is 8. And then plus 24. And then we're going to distribute the negative. So we get 9/2 positive. And then 6 times 3 times -1 is -18. Simplifies to 6.5 or 13/2. So the area under the curve is 13/2. All right, last one. So remember, if we are determine the velocity of the particle at time t is equal to 7, okay? When v of 4 is equal to 5 and the acceleration is equal to negative sine x squared plus 1. So there's a lot going on here. And what I would like to do is evaluate, I'm going to use what I know about definite integrals. So I'm going to start with the integral from a to b of a of t dt is equal to the velocity of t evaluated from a to b. Okay, so we're doing v of b minus v of a is really what we got. Okay, so I'm just going to check out this equation that I have here. The velocity of b minus the velocity of a. And I know two things. I know what a of t is, and I know what v of 4 is equivalent to. What I don't know is what v of 7 is equivalent to. So this, when I get the velocity of v of 7, which is going to be my b value, or when I plug in 7 into the velocity equation, I get the velocity of 7, or velocity at time is equal to 7. So I'm going to call my a value 4. We're going to find the area from 4 to 7 of a of t. So negative sine of x squared plus 1 dx is equal to the velocity of 7 minus the velocity of 4. And we can really substitute in everything except for this velocity of 7. I do not have my calculator app on my computer right now. So we're going to use a calculator to evaluate the, I know this sounds crazy, to evaluate the function negative sine, the integral of negative sine x squared plus 1. So we can do definite integrals on the calculator. What you do is you press math. Okay, you're going to press math, and then go scroll down to 9, which is fint. And it should bring up a integral where you have to plug in your a, your b, your function, and then let me double check that. Math. Yeah, and then your variable of integration, okay? So we would just plug it in exactly like it looks like up here. And when I do that, I got 0.1067 ... And then, so that's going to equal v of 7 minus v of 4. So how do we solve for v of 7? Well, we just add v of 4 to both sides. So we're adding our starting value to both sides. So I get v of 7 is equal to, and I had a value for v of 4, which was 5. So I just do 5 plus 0.1067 ... So v of 7, well, I'm going to run out of room, is about equal to 5.106, or if you rounded, 5.107. Okay, so these types of problems where you're given a starting value and you need to get the ending value, or they're giving you the ending value and you have to get the starting value. I call these problems spam problems. It equals start plus accumulation method. Spam. So we start with, like I said, the integral from a to b, so the area under the curve of your function, and that is going to equal the velocity of the net change of velocity. Okay, and what I did was I just added v of a to both sides. So I get v of a, which is the starting velocity, plus how much change we had, is equal to our ending velocity. Okay, this is in terms of velocity and acceleration, but if you just are using like regular old f of x notation, we'd say f prime, the integral from a to b of f prime of x dx is equal to f of b minus f of a. A is our starting value, so we're going to say f of a plus the integral, so this is our start, plus our accumulation. This is basically the change in y, okay, from x equals a. So we do f of x dx is equal to f of b. It will give you the ending value. That's it.